Hi, folks. Glad to have you back again for episode 4 of Applications of the Derivative. Well, anyway, this is what we've been working for. Not the whole semester necessarily, but, well, yes, optimization problems. That's the reason why you would be taking calculus if your major is business or even something similar to that. So let's get with it. It's been a while. We're going to solve some real life optimization problems. That's it. Now, what I've got, you won't see a lot of writing on the screen this time because I've spent a lot of time up front changing the slides so that it's even a little bit better than my writing, because things are going to come piece by piece. So be aware. So one of those things we need to do for business or an assorted array of applications is find the best values. That's minimum or maximum values. And we're going to look at an example here. So here's an example. It doesn't really have much to do with application, to do with business exactly. It's a box, but it's we're getting there. So here's a box. Take a notice of several things in particular. One, the bottom is square. X by x square. It's h inches or whatever it is, 8 inches high. So the surface area is, on the bottom, it's just x times x, length times width. On each of those sides, you've got x times h. And you got 4 of them. So that means 4xh. So here's your surface area. Imagine, for example, you're painting it or you're creating the box. That's how much area you'd have to cover or create. And here's this 108. If you paused, which is a good idea, the surface area or the amount of material you're going to use for this box is 108 square inches. And here you've got a formula about the surface area. Now, what we want to do is we want to make the box that holds the most material of whatever it is. Even if it's something that has concrete sides and you're filling it with water, like in a very small swimming pool, maybe for a mouse, right? Anyway, the volume is very simple. Remember the box? I'm not very good at drawing here, but you get the idea. Got x length, x width, h height. And there's your volume. Now that's the primary equation because V is what we want to optimize. We've also got something about surface area. We're going to use that as well. This is the secondary equation. This is not what we're optimizing, but instead we've already decided how much material we're going to use. It's a secondary equation. Remember, the primary one includes the parameter that we want to optimize. So we'll express that as a function of just one variable. Now if you notice back over here, you look at one of these, we've got x, h, and v. Down here you've got x and h. We want to sort of reduce this, in a sense, to only one variable, in particular x. So we're going to solve the secondary equation because we're going to stick with the primary one. This is a version of that secondary equation. Here it is. I put it here for your convenience. Solve that for h, and there's your secondary equation with just a slightly different look. Now what we're going to do is we're going to take h, which is the same as this, and we're going to put it in the primary equation by substituting. So here's the primary equation. One too many variables, you might say. And we're going to replace h by 108 minus x squared over 4x. And there you go. Simplify that a bit. And this is another way of writing the volume, taking into account how much surface area we have and how it's calculated. Another thing you need to check on in this type of problem is what x's can you actually use? Because sometimes negative values don't make any sense. For example, if you're a manager and you're trying to decide how many people you need on the next shift, well, it really wouldn't make any sense to have a -3 people on the next shift. It wouldn't make any sense to have 7 1/3 people on the next shift. You have to think about what the feasible domain is. What is your application? What are the parameters of such application? So in this case, remember we've got the box, and we're going to use 108 square inches to make the box that holds the most stuff that we can. Well, it has to be non-negative. A negative volume doesn't make any sense, a negative area doesn't make any sense, and a negative bottom of the box doesn't make any sense either. There's no such thing. So x is positive for one thing, and also because if you remember, this x is related to the 108, it also means that x is less than or equal to the square root of 108. All right, with that set up, you can use that equation that we got just a moment ago. You want to look back here a moment. There we go. There's our equation, 27x minus 1/4 x cubed. Want to write that down? Okay. I'll go back where we were. There we go. Using that and taking the derivative, take the derivative dv dx, and then setting that equal to 0, you get two possible x's, 6 and by extension h equals 3. So there is your maximum volume for using 108 square inches for your box. So here are some steps or some guidelines. So first of all, what do you have? What are the given quantities? And what quantities do you need to find out? And by all means, if at all possible, draw a picture. It helps in almost every situation that a sketch is possible. Second, write a primary equation. Remember, you're looking at the quantity that you're maximizing. In the previous case, it was volume. So you want the primary equation to have the volume in that case. Next, if there's a secondary equation that's possible, write that out and solve it for one of the variables in the other equation. What is the reasonable domain of the primary equation. What values actually make sense? And then find out the maximum or minimum value using the calculus methods you've already got. So here we go. We're going to try another one. We're going to create a rectangular page. Remember, sketch. You're going to have 24 square inches of print inside. Print. Excuse me. Notice you're going to have margins. That's not part of the print. The print is on the inside like that. And there's where the print is. And you've got margins. And it tells you here what the margins are, top and bottom, 1.5 inches. On each side, 1 inch. Gives you a bit of white space. What dimensions of the page? That's the whole thing. What dimensions does this need to minimize the amount of paper? Well, of course we want to minimize the amount of paper. The more paper we use, the more cost there is, and the smaller the profit. Remember, profit equals revenue minus cost. If we keep this low, then this will be higher. So here's a picture you could draw. Get accustomed to drawing pictures. Here's the printing area right here, and we're going to, since we are looking for these, we want as much print space as possible. So we'll call one side X, one side Y inches. Add in our margins, 1 inch on each side, 1.5 inches top and bottom. And that way the area of this whole piece of paper will be X plus, or excuse me, Y plus 2 across here. Because here's Y, and you've got 1 inch on each side, so Y plus 2. On the other end, you have X in this direction, and you have 1.5 inches up here, 1.5 inches down here, and there's your X plus 3. And those are the two dimensions of the piece of paper, and the area that you want to keep as small as possible to save paper. So since this is what you want to minimize, that's your primary equation. The fly in the ointment right now is you've got two variables over here. You only want one, really. So what do we have? The printed area is 24 square inches, and that's X times Y. There's your secondary equation. Now, if you want this all in X's up here, then we'll solve this one for Y. Solving that for Y, you have Y equals 24 over X. And now what you can do is you can take this 24 over X, put it in your primary equation, and now your primary equation for A, the area, printable area, has only X's in it, no Y's. So after substituting, this is what you've got. Simplify a little bit using the common denominator of X. Remember, this will make it 2X over X. That gives it a common denominator. There's your 24 plus 2X and your common denominator of X. Multiply and divide each term by that X. Simplify as much as possible. Now we're ready to differentiate with respect to X, because this equation, the primary equation up here, is a function of x. So we're going to find dA dx. And since we want to minimize that area, we'll then set it equal to 0. X has to be positive. Remember, we have to check and see what makes sense for x. That way, when we get to the end, we can take a look at step number 4, or whichever you name it, and say, oh, those negative values, forget them. 0 values, forget them. The positive values, that's what we'll have to look into. So here's the derivative. Not too hard, right? Set that equal to 0. Solve for x. There we've got x squared equals 36. That should be easy to solve. Plus or minus 6. But remember, what's the feasible domain? Positive values. We have to throw out the x equals negative 6. Here's your critical number. So A is a minimum at x equals 6. And remember, we're looking for this size of the paper. So the paper is going to be x plus 3. That's 9 inches. And the width is going to be y plus 2. Remember, y was 24 over x. So y plus 2 is 6 inches. So that's going to save us the most paper and get us the printable area that we actually need. So these are very simple. Sometimes the primary equations are a lot more complicated, but it's the system you need, the plan you need. And once you've got that, just stick with that and be careful with the calculus. And the next thing you know, you're going to be doing some really awesome things with calculus and with the business applications. Here's a picture of what these look like. Here's a picture of what the volume equation looks like. We had originally, the first one, remember that? We're trying to maximize the volume, and there it was, 6108. And the second application we had, we were trying to find the minimum paper that we needed, and there's our minimum value right there. Well, folks, that's a simple start, and you just need a bunch of practice. But these are the basic principles. Stick with those, and you can do fantastic things. Well, you keep smiling, and I'll see you soon in the class. Bye.